What is up, guys? This is Weasel for PokerWeasel.com. Welcome to part 5 of the Core Maths series. Today we're going to be talking about probability. In this episode we are going to cover all of the basic information you need to know regarding probability, such as why you use probability, how we can calculate the probability of successive events, working with limited sample sizes of data in the case of utilizing HUD stats where we don't have a big sample, and we're also going to talk about weighted bluff frequencies, commonly referred to by many poker players as Bayesian probability. So first of all, why are we interested in probability? Why is this an important part of the Core Maths series? There's at least 2 good reasons why poker players should be familiar with basic probability calculations. Number 1, probability is needed in EV calculations. EV, or expected value, is one of the main languages of poker. It essentially tells us how much money our decisions make on average. And in order to make effective use of EV calculations, we're going to be working with probabilities. The next part in this Core Maths series deals with how to make EV calculations. Some of that video will not make sense if you haven't understood the basics of how to work with probabilities. So the information you learn in this video is going to help you in the next video in the series. The second reason is that understanding probability and frequencies is needed in order to interpret and utilize HUD stats. So if you want to be good at figuring out exploitative opportunities by looking at your opponent's stats, you're going to have a basic understanding of probability. Probability is closely related to frequency. So if we say, for example, that a player folds with a 50% frequency to a flop c-bet, it means there's a 50% chance or probability that he's going to fold. These are essentially one and the same things for the most part, and understanding probability is going to help us make very good use of our HUD stats. We're not going to do anything super complicated in this video. We're going to start out right at the basics and cover everything you need to know on a very basic level regarding probability. So one of the first things that we learn about probability in general is the probability of successive events. So what do we mean by successive events? Very simply, the probability of event A, let's just call it event A, occurring followed by event B occurring. So both of these events happen and we want to calculate the probability of it. Now here we can see a representation of how mathematicians often represent probability. You see we have a P with an A in bracket. Now that P is not really part of the formula, it simply means probability of, and then the event is in the bracket there, so probability of event A. So you can see we also have probability of event B here in this formula. That sign in the middle means multiply. Essentially, the probability of one event occurring followed by another event occurring can be ascertained simply by multiplying their respective probabilities. One thing we may have picked up already through this course is that when working with probabilities, we usually want to use them in their decimal format, i.e. 50% is represented by 0.5, for example. So we convert the probability of event A into a decimal, the same with event B. We multiply them together, and the resulting decimal is going to give us the probability of both events occurring. So let's just take a very simple example. You probably already know enough in order to calculate this, even if you've never had any exposure to probability before, because it's very simple. Here's the question. We flip a coin twice. What is the probability of it landing on heads both times? So we have event A, which is the coin landing on heads, and event B, which is the coin landing on heads again, essentially. So what is the probability of a fair coin landing on heads? Hopefully we know that it's 50%. It's going to land on heads 50% and tails 50% of the time. So probability of heads, 50%, expressed as a decimal, that is 0.5. And we also know that the probability of it landing on heads again is still the same. It doesn't change, by the way. This is a common fallacy regarding probability. Just because we've already got heads doesn't mean it's more likely to land on tails the next time. You see this kind of fallacy appearing throughout players' games, especially if they have mindset issues. They think, for example, that because they've got kings twice and their opponent has had aces both times, that the next time they pick up kings, it's less likely that their opponent is going to have aces. They feel as if luck evens out over the short term in such a way, but it doesn't. Luck has no memory. That's a very important concept. So here, just because the coin's already landed on heads doesn't mean it's less likely to land on heads the second time in a row. That probability is still 50%. it lands on heads again, the probability of it landing on heads again is still 50%. Luck has no memory. So we know probability of event A, 0.5, multiplied by probability of event B, 0.5. So the probability of a coin landing on heads twice in a row is 0.25, or expressed in probability format, percentage format, we multiply the decimal by 100 to get 25%. So we can see a very simple example of calculating the probability of successive events. You just multiply their respective frequencies or probabilities when expressed as a decimal. Okay, let's move on to another example. This example is slightly more complicated, but only ever so slightly, and it's going to be poker themed this time, so we can see an application of this information to a real poker situation. Here's the question. We open raise from the button, so it's a standard still situation. It's folded around to us pre-flop, and we open raise from the button, probably hoping to pick up the blinds. How often do the blinds fold? Well, small blind folds 80% of the time to a button steal, and big blind folds 65% of the time to a button steal. So what is the probability that both blinds fold? So hopefully we can see this idea of calculating the probability of successive events. The chance of event A occurring multiplied by event B. Event A is a small blind folding, which happens 80% of the time, and event B is big blind folding, which happens 65% of the time, assuming small blind's already folded. So here are the probabilities represented in decimal format. Probability of small blind folding 0.8, probability of big blind folding 0.65. We then multiply those together. 0.8 multiplied by 0.65 equals 0.52, or 52%. We've essentially just done the same maths, apart from now it's poker themed, and hopefully you can see an application of this information to a real poker situation. So this is a very common situation in poker. We're on the button, we're facing two opponents in the blinds, we want to figure out how wide we can go. And just as a really rough guide, we know that if both blinds are folding cumulatively above 60% of the time, then we should be able to open raise profitably any two cards on the button, although it does depend partially on our button open raise sizing. But now using this information, you know how to calculate exactly how often the blinds are folding cumulatively. You can simply take their respective folding frequencies, expressed as a decimal, and multiply them together. And you get to figure out whether you can generate automatic profit with an open raise. So we can also see how a knowledge of probability can help us to utilize our opponent's HUD stats and generate exploits. Okay, moving on to our next example. Notice that we're still working on this theme of probability of successive events. This question is just going to be slightly harder than the previous two. However, you should be equipped with the knowledge you need in order to answer this question, even if you had no prior knowledge of probability. So I recommend you take a go at answering the question first. Then if you can't answer it, or if you have successfully come up with an answer, then continue with the video and verify whether your answer was correct. Here's the question. We draw 3 cards from the deck. Plain deck of cards, 52 cards in the deck. We draw 3 of those cards. What is the probability of all 3 being spades? We need to notice a couple of things. First of all, we have 3 successive events here. So how does it work in the case of 3 successive events? Exactly the same way. Probability of event A multiplied by probability of event B multiplied by probability of event C. Very, very straightforward. But we also need to figure out how we can assign frequencies or probabilities to drawing those specific cards from the deck. And a key piece of information that somehow some players seem to lack is a knowledge of simply how many cards there are in a deck of cards and what the distribution of those cards is. And it's very, very simple to learn. There's 52 cards in a deck. There's obviously 4 suits, so that means that there are 13 cards in each suit. So think about this for a minute. What is the probability of just taking one card out of a deck of 52 and that card being a spade? Well, we know there's 52 in the deck. We know that 13 of those cards are spades. Therefore, the probability is 13 out of 52. Let's see that visualized. Probability of card 1 equaling a spade, 13 out of 52. Now, why does it say 13 out of 52 and not a probability? For example, it could just say 25%. Or it could say 0.25. We're used to those formats. We might not be used to this format of representing a probability. This is what's referred to as fractional format. It's slightly different from ratios. There's a very, very key difference. This is not the same as a ratio of 13 to 52. It's actually the same as a ratio of 13 to 39. What's the difference between a fraction and a ratio? Very simply, in fractional format like this, that larger number also includes the smaller number. So that 52 includes that 13. Whereas in a ratio format, it would be 13 out of 39, because the larger number would have the 13 not included within it. So it's very important that if we want to be good at probability, we understand both fractions and ratios. So this is a fraction, and even if we're not 100% familiar with the concept of fractions, we probably use them in our day-to-day speech. For example, we might say something happens a quarter of the time, or something happens a fifth of the time, or something happens half of the time. These are fractions. Quarter is represented by 1 over 4, half is 1 over 2, a fifth is 1 over 5. And when we look closely at this fraction here, we can say that this fraction is not expressed in its simplest format. This fraction can also be expressed as 1 over 4, or a quarter of the time. And that's because both numbers in the fraction are divisible. Both numbers can be divided by 13. If we divide 13 by 13, we get 1. If we divide 52 by 13, we get 4. So when two numbers of the fraction are divisible by the same number like this, they can be expressed in a simpler format. In this case, 1 over 4. It makes sense because we know that there are 4 different suits in the deck, equal amounts of cards in each suit. So the chance of drawing a card from one of those suits has to be 1 over 4. So let's imagine we've taken a spade out of the deck now. What is the probability of taking a second spade out of the deck? Is it still 13 out of 52? Well, remember that we used the number 52 because it represents how many cards there are in the deck. But now we have a deck of cards where one of the cards has been taken away from the deck. There's only 51 cards left in the deck. And how many spades are there? Are there still 13 spades? There's not. There's actually 12 spades now. So the probability of card 2 being a spade is no longer 13 out of 52. It's actually 12 out of 51. After we've taken that second spade, what is the probability of drawing a third spade from the deck? You probably know the answer already. It's now 11 out of 50. There's 11 spades left in the deck, and there's only 50 cards left in the total deck. So every time we successfully retrieve a spade from the deck, it makes it a little bit less likely that the next card we take is also going to be a spade, because there's simply less spades in the deck. So we have our 3 probabilities of event A, B, and C. We just need to multiply them together. But how can we multiply fractions together? Well, on some scientific calculators, you do have the option to input a fraction. You'll see a button which says A over B. You input the first part of the fraction, known as the numerator. You press the A over B key. Then you enter the second part of the fraction, known as the denominator. Just looking at this scientific calculator we have up here on the screen, it doesn't seem to have that feature, although it might be possible to enable it somewhere. So is there another way that we can use these fractions, assuming that we don't have that A over B key? Well, we can simply convert the fractions into decimals by dividing the smaller number by the bigger one. So 13 over 52, what is that when expressed as a decimal? We just do 13 divided by 52, and we can see it's 0.25. We probably could have guessed that anyway, because we did say this can simplify to 1 over 4, which we probably realize is 25% of the time, or 0.25 when expressed as a decimal. The ones that might be a little bit more complicated are things like 12 over 51. This is actually already in its simplest form. Let's try that on the calculator. 12 divided by 51. We're probably going to get a complex looking decimal right now. There you go. You can see 23.529411. Very, very complex answer to that question. We'd usually simplify that when using it in a calculation. Perhaps we might take 23.53 or something. Notice that it's 23.529 when multiplied by 100. So we have to simplify this at some point, which means we're not going to list all of these decimal places. So let's say we want to do it to 2 decimal places. So we could put 23.52, but seeing as it's 23.529 and that third decimal place is 5 or higher, we're going to typically round the number up which occurs before it. So rather than 23.52, this often gets simplified to 23.53 because it's almost 23.53. It's 23.529. Okay, so we'll do the same with 11 divided by 50. And ideally you'll be writing these down or saving them, but I know they're stored in the PowerPoint. So that's 0.22. Let's just check our maths here based on our calculations. There we go, we can see 0.25 multiplied by 0.235 multiplied by 0.22, and there is our probability, 0.0129 or 1.29%. So this shouldn't surprise us. And one thing that's always important to do when you are running mathematical calculations is just to run a verification check in your head regarding the result that you've produced. For example, if we ran the numbers here, let's just say we did the calculation and we got the value 75%. We should already be able to see that that's very, very unreasonable, because when we think about how likely it is that we take 3 spades in a row out of the deck, it's certainly not 75%. It's actually going to be more likely that one of the cards is not a spade. This is actually a very unlikely outcome. If you don't believe me, go and get a deck of cards and see how many times you draw 3 spades in a row from the deck in the next hour. So 1.29, that passes the verification check. We know this is going to be an unlikely event, so that number looks realistic. So always make sure you run this check regarding your answers. Don't just take any value and say, oh, well, I've done the maths. Apparently there's an 85% chance I take 3 spades out of the deck in a row. That's clearly not right. Something's gone wrong with the maths there. Okay, moving on. One final probability of successive events question. This is going to be the hardest. You may not be able to solve this on your own unless you already have some prior experience with probabilities, in which case it should be reasonably straightforward for you. So we are all in on the flop with a flush draw. What is the chance that we hit by the river? Now, of course, most of us already have a way of calculating this that doesn't involve using the method we're looking at, which is to use a 2 times and 4 times rule. So most of us know if we have 9 outs on the flop, what is our chance of hitting by the river? We know it's going to be roughly 36% of the time, although not exactly. So we already know what kind of answer we should be getting as a result of our calculation here. We know what we're working towards. So think of the question this way. Can we demonstrate that the 2 times and 4 times rule is accurate and equals roughly 36% in this case, by multiplying the successive events involved? So let's think about what the successive events are. Now we have a little bit of a problem here, because we can hit our flush on the turn, so we can figure out the probability of that happening quite easily. And then we could also hit our flush on the river. But you see, if we just multiply those 2 successive events, what we're basically saying is, what is the probability of hitting our flush draw both on the turn and the river? In other words, let's say we have a spade draw. We're actually now just calculating what is the probability of a spade falling on the turn and the river as successive events. We don't want that. We're interested in the probability of one of these spades falling on either the turn or the river. So at first glance, this is not a straightforward problem, but there is a trick we can use to calculate this. Let's try and think of everything in reverse. What is the probability of us not making a flush in this case? And that's the clue you need to really solve this problem. Once you think about the problem in this way, you'll find this very, very straightforward. Because then we are interested in successive events. We're interested in the probability of event A being the turn doesn't complete the flush, followed by event B, which is the river doesn't complete the flush either. Let's have a look at the maths here. Now, we have to keep in mind that we're not working with a 52 card deck. Why not? Because we already know some of the cards are not in the deck anymore. We know the values of our 2 cards, we know the values of the 3 cards on the flop. Furthermore, we know that of the 5 known cards, 4 of those have to be suited to the flush. That means of the original 13 cards that could be used to generate that 5 card flush, 4 of those are no longer in the deck. In other words, we have 9 outs to make our flush on the turn or river, and 47 of the 52 cards in the deck are the ones that remain unknown. So what is our chance of not making a flush on the turn? Well, you can see it there on the screen, 38 of 47. 47 unknown cards left in the deck, and 9 of those allow us to make our flush, so the remaining 38 cards are cards which cause us to miss our flush on the turn. So assuming now that we miss our draw on the turn, what is the probability of us proceeding by also missing our draw on the river? Well, there's still 9 cards in the deck that can make our flush on the river. But there is one less card in the deck because one of the cards has fallen on the turn. It didn't complete our flush card. So instead of 47 cards left in the deck, there's now 46 cards left in the deck. But 9 of those make us our flush, which means by deduction 37 of those cards will miss our flush draw on the river. So here we have now our two probabilities. Probability of event A, 38 out of 47. Probability of event B, 37 out of 46. We multiply those two together and we get this value, 0.65. So is our probability of hitting by the river 0.65? No, remember this is our probability of not hitting by the river. So if our probability of not hitting is 65%, what is our probability of hitting? Well, by a simple process of deduction, we can see that we're going to hit our flush draw around about 35% of the time. That pretty much confirms that the 4 times rule is at least close to being accurate in this case. We can see that by the 4 times rule to get the value of 36, the actual value is 35. I'll just confirm that using my calculator. Probably some simplification occurred here with that number. So 38 divided by 47, let's convert that into a decimal. Now to avoid any premature rounding errors, we can just add this to the calculator's memory, so I'm going to press the M+ button there. 37 divided by 46 is our second probability. And we're going to multiply that by the value stored in our memory, so I'm going to use MR for memory recall. Go to equals 0.6503. So you can see if we rounded that to 2 decimal places, it would be 65.03%. Let's move on to our next example now, where we'll talk about the probability of cumulative events. What's the difference between successive events and cumulative events? Well, for successive events, we wanted to know the probability of event A happening followed by event B happening. In the case of cumulative events, we want to know the probability of event A happening or event B happening. Let's see a worked example of this. We have a 6-sided die, or dice as most people call it, although the singular is die. Probability of it landing on 2 or 5. So we have a regular die, 6 sides. What is the possibility of it landing on either 2 or 5? Well, what is the probability of the dice landing on 2? Well, assuming the die is fair, there are 6 sides. Therefore, the probability of it landing on 2 is 1 in 6. What is the probability of it landing on 5? Well, it's the same, 1 in 6, assuming that the die is fair. Now, in this case, do we multiply these fractions together? No, we would do that if we were interested in the probability of the dice landing on 2 and then on side 5. But actually, we're interested in the probability with one roll of the dice if it's going to land on either 2 or 5. We can calculate that by just adding the respective probabilities together. So we have 1/6 plus 1/6 equals 2/6. Now the rule with fractions is when the denominator is the same, the second number there, the 6, when that number is the same, it's okay for us to add the first number together, the numerators. So because both of these are fractions where the denominator is the same, we can add those two ones together. So 1/6 plus 1/6 equals 2/6. Now when we have this fraction 2 over 6, this is a non-simplified fraction. Both of the numbers in that fraction are divisible by 2. 2 divided by 2 is 1, 6 divided by 2 is 3. So we can simplify that to being 1/3 or roughly 33.33% of the time. So it's important for us to be discerning when we're faced with any question to do with probability. Is the question asking us for the probability of successive events or cumulative events? As a really general linguistic guideline, if we're looking for the probability of one event occurring and another event occurring, i.e. simultaneous or successive events, then we're generally going to multiply the respective probabilities. Whereas if we're interested in the probability of either one event occurring or another event occurring, then we generally add their respective probabilities together. At this stage, let's talk about using probabilities with limited sample size. It's best if we illustrate this with an example. Let's imagine we 3-bet an unknown villain and he folds twice in a row to a 3-bet. We don't have any other history on the guy, but we've 3-bet him twice and both 2 times he's folded. Now imagine we're in another situation where the same villain and we're thinking about whether we should 3-bet the 3rd time in a row. And we check the HUD stats we have on him, and his fold to 3-bet stat is 100%. And that's because we've 3-bet him twice and he's folded both times. Let's assume no one else has 3-bet him, just us. So it's 100% fold to 3-bet, but obviously the sample size there is 2 of 2, so not a very big sample. Now the question is, can we use that information to make a decision? Because the way many players will approach that is they'll look at that and say, well, I can't really use that information. It's only 2 of 2. The sample size is not big enough. I'm just going to stick to my default game plan. So what ends up happening is they play another 5,000 hands against that villain until they reach a point where they're happy with the sample size. So now the guy's folded 50 out of 60 opportunities, and now the player's thinking, okay, now this sample size is big enough. I'm going to start 3-betting this guy light. But with there, we have a sample size of 2 out of 2. Let's think about a couple of questions regarding that small sample size. Question number 1, can we prove that villain is folding too much to 3-bets? It's very important we're clear here that the answer is absolutely not. We don't have a big enough sample size. In fact, to prove anything in poker, to prove someone's folding frequencies, to prove what our win rate is, we need a huge sample size of hands because there's so much variance in the world of probability. So can we prove that our opponent is folding too much to 3-bets? Absolutely not. We don't have a big enough sample size. But here is where players make the mistake. They think, oh, well, given that we can't prove that he folds too much to 3-bets, we should just stick to our default strategy. But you see, as poker players, we don't need to prove stuff in order to make a logical exploitative adjustment. Think about the second question. Can we use the information to make an exploitative adjustment? Well, imagine you were asked to place a wager. You're going to bet $100 on 2 outcomes. Outcome number 1 is that over a big sample, this guy turns out to be a huge calling station against 3-bets. He's actually only folding 20% of the time to a 3-bet, and it just so happened that he had the bottom of his range the last 2 times we 3-bet him. Or would you wager that actually it's more likely this guy turns out to be a guy who just folds way too much to 3-bets? We can't prove that at this stage, but given that he's already folded 2 of 2 to our 3-bets, it's actually more likely this guy is too tight against 3-bets as opposed to being too loose. Hopefully we can see the logic in assuming that it's more likely that in the long run this guy is going to fold too much against 3-bets. So can we use that limited sample size of information to make an exploitative adjustment? Absolutely. We're probably going to 3-bet bluff against this opponent more often than we would do against an average unknown. How wide should we go though? We see a guy's folding 2 of 2. Should we suddenly just start 3-betting any 2 cards, assuming that he's folding way too much? Probably not, because the quality of our information there is not very good. The sample size is very limited. So we can use that information to make exploitative assumptions, but we don't want to push that out too far given that the sample size on the information is limited. So the size of the adjustment we make will depend on our level of certainty. With 2 of 2, we think it's possible he's folding too much, but we're not overly certain about that. We just don't have a big enough sample size. Whereas if the guy's folded 5 of 5, we might push our 3-betting range a lot wider in that spot. We still can't prove that he's folding too much, but the level of certainty we have regarding his folding frequencies is going to increase alongside the sample size. Eventually it's going to get to a point where you do have a pretty big sample and it's obvious the guy's folding way too much, at which point you can push your exploit all the way out there. You can literally be 3-betting the 7 deuce offsuit if it's appropriate because you know villain's going to be folding too much to your 3-bets. So the mistake here is not using information we have on our opponents just because the sample size is limited. You should absolutely use small amounts of data to make exploitative decisions, but the size of the adjustment will be related to the sample size and it's going to depend on our level of certainty as a result of that sample size. So hopefully now you can avoid the mistake many players make, which is waiting to have a sample size on your opponent's HUD stats before making any move exploitatively in a certain direction. As soon as you start getting a feeling for what your opponent's doing wrong, you should be attacking that leak. Okay, let's talk about weighted bluffing. Now, the majority of poker players refer to this area of probability as Bayesian probability. I'm not really 100% convinced it really falls into the category of being Bayesian probability. It seems far too simple. If you've ever done anything with Bayesian probability, even the simplest versions of Bayesian probability use somewhat advanced formulas, or at least it seems that way. So this almost seems too simple to be referred to as Bayesian probability, so I might contest that to some extent. But I think the best way of explaining what Bayesian probability is this idea of weighting certain probabilities or frequencies by additional information we have on a certain topic. And if you take that definition, then you could call this Bayesian probability. Let's have a look at an example and we'll see how that applies. So here's the question. Villain bets the river with a polarized range. Okay, so he has a strong value component to his range, he has a bluff component to his range. He bets half pot. Let's just say that we know from a large sample size of hands that his average bluffing frequency in this spot is 25%. So the question is, should we make the call? Well, in terms of pot odds, which we learned earlier in the series, if we're facing a half pot bet and contemplating a call, we need at least 25% equity to be good. So if we assume we have a bluff catcher here, it means that the call is going to be exactly break even. We need 25% equity to make the call. We are good 25% of the time because that's how often our opponent is bluffing. Now notice what we've put here in this bullet point. It says, assuming no information regarding the board run out, we are faced with a break-even call. Because this is not the only information we often might have in a certain poker situation. Perhaps we know how often our opponent bluffs, roughly, if we have a big enough sample size. But that's not the only information we have. We can also see how the board run out relates to our opponent's range. So there are going to be some board runouts where our opponent just doesn't have a lot of bluffs. Is he still going to be bluffing 25% in this case? Probably not. Whereas there's other situations where all of his draws miss on a certain board runout, there's a good chance that he might be bluffing more than 25% just because he has so many busted draws in his range. So how can we weight our decision here based on the quality of the board runout? Well, this is where the application of Bayesian probability comes in. So imagine this. We catch a runout which is especially good for villain's range. He has 20 potential bluff combos, which is not that many by the way, and 20 strong value hands. Now of course, if he were to bluff all of his bluff combos, we'd still be good 50% of the time and we should make the call. We are going to assume, however, that when he looks down at a possible bluff candidate, he's going to fire that bluffing hand 25% of the time. So that's going to be roughly equivalent to him actually bluffing only 5 combos, 25% of his 20 total combos. So he's going to have 5 bluffs and 20 strong value hands. So 5 out of 25 are going to be bluffs. That translates to a 20% bluffing frequency. He's making a half pot bet, so we need to be good 25% of the time to call, assuming we have a bluff catcher. You can see, because the runout's so good for villain's range, there's a possibility that he's not going to be bluffing with a high enough frequency. So we've used a weighted probability calculation there. Now just so we're clear here, a very, very good player will understand that a certain board runout is very good for his range, and he will dig very deep to find enough bluff combos. So you may find that his bluffing frequency is quite similar on a large number of different board runouts. But this is a bit different from the average player who just looks at the hand, decides whether it's a good bluffing hand, then makes a decision whether or not to bluff. So in situations where they don't have a large selection of possible bluffs, their bluffing frequency is simply going to be lower than their average bluffing frequency. Let's see the reverse of that, which is we catch a runout where a large number of draws brick for villain. Perhaps there's a double flush draw out there on the turn, there's a bunch of straight draws. Everything bricks on the river. So when we look at the distribution of his range on the river, let's say he has 80 potential bluff combos and 20 strong value hands. We know he's the kind of guy that likes to bluff about 25% of the time when he looks down at a potential bluff combo. So roughly 1/4 of the time. So that means out of the 80 potential bluff combos, 20 of those are going to be fired. So his bluffing frequency is 20 out of the 40 combos he bets. That's a 50% bluffing frequency. So because the board runs out in such a way that he has so many busted draws in his range, there's a very, very good chance that he's going to end up bluffing a lot higher than his average bluffing frequency. Of course, once again, a very good player will not do this. I'll look at this situation and say, wow, I have a very large number of bluffs in my range. I can't fire them all. I'm just going to check fold a larger number of my busted hands so that my bluffing frequency is balanced on the river. So understand that very, very good players will adjust based on the quality of the board run out. But the average player doesn't do this. So that means on board run outs that are very good for their range, they're usually going to be under bluffing. And on board run outs which are very bad for their range because everything bricks, they're usually going to end up over bluffing. They just have so many different bluffs to choose from. Okay, so that's all of the basics on probability. You won't need much more than that for most poker calculations. This is what you should be able to do after watching this video. Probability of successive events, sometimes called simultaneous events, i.e. one event happens following another event. We just multiply the respective frequencies or probabilities of those events occurring. Probability of cumulative events. This is where either one event occurs or another event occurs. And what we do in this case is we add the respective probabilities together. Working with limited samples, we've seen an application of probability to figuring out how we can use limited sample sizes of information. By the way, most players don't really understand this. Even to the point where a lot of guys will actually tell their tracking software to not display stats when those stats are based off a sample size beneath a certain number. So while that might seem logical, based on what we've seen in our discussion on working with limited samples, we've seen that even a small amount of information is useful so long as we don't put too much stock into it. We don't want to over adjust based on very small samples, and that's another league players sometimes have. They see the guys fold into a 3-bet 1 of 1, so they start 3-betting the 7-deuce offsuit. That would be an example of over-adjusting based on a limited sample. So as our level of confidence in our opponent's tendency increases along with the sample size, so does the size of the adjustments we can make in order to exploit our opponents. Finally, we've seen an application of Bayesian probability. As mentioned, I have doubts whether this really constitutes Bayesian probability, but it's generally referred to as Bayesian probability by the majority of poker players when they discuss similar river situations. So you've seen a very, very simple application of Bayesian probability. By the way, it's a very interesting branch of mathematics. So if you're bored and you really like to learn about probability, then I recommend you run a Google search for Bayesian probability, and I think that will probably kill the next 10 to 15 hours of your life, so have fun with that. Alright, thanks very much for watching this video. Hopefully you feel a bit more comfortable using probabilities and frequencies after watching this. There's going to be more application of probability theory in the next video because we're going to be talking about running EV calculations. As we mentioned at the outset, this is one of the core fundamental underlying languages of poker. What is the expected value of each of our decisions? So we're going to find a little bit more on how we can run those calculations in the next part of the series. So thanks very much for watching. Catch you in the next part of the series. This was Weasel for PokerWeasel.com.